Welcome, guys. In this series, we are taking you from zero to complete mastery of regular expressions in theory of computation. Here's our full roadmap. This video will lay a solid foundation covering the core terminologies, the three operations, and some extension to regular expressions, and the three categories of exam questions that you are likely to face. What are regular expressions? A regular expression is a formal mathematical notation used to specify a set of strings over a given alphabet. It defines a pattern that describes or matches a specific formal language constructed using basic operators like the concatenation, choice, and repetition. So to lay the foundation, we are going to cover some basic terminologies in relation to regular expressions. One is the symbol. So a symbol is an atomic building block or character used to construct strings. So it can be any symbol at all. An example is 0, 1, AB, plus, and so on and so forth. It can be any digit, any symbol at all. Alphabet is a non-empty finite set of symbols. It's represented with the sigma, the Greek uppercase letter sigma. Examples are binary alphabets, which consist of 0 and 1, and English alphabets, which consist of A to Z. So you can imagine being in a different world where you can only use some set of symbols. So those set of symbols are our alphabets. String, denoted by small letter W, is a finite sequence of symbols chosen from an alphabet. Example, over the alphabet 0, 1, we can have valid strings like 0, 1, 0, 1, 0, 0, 1, 1, any possible combination of the symbols in our alphabet. Language, a formal language is a set of strings over a given alphabet. So an example can be a language of words such that the word begins with 0. Here, word refers to strings. Another name for string is word. So a string that begins with 0, it can be 0, 0, 1, 0, 0. So all these ones will be accepted by our language. So in relation to our normal English grammar, you can think about it this way. We have individual characters like A to Z. Those are our symbols. When we group all 26 letters together, we get the English alphabet. When we take letters from that alphabet and string them together, we form words, which we call strings or words in this context. And when we collect all valid words that follow the rules of English grammar, we get the English language. The empty set is a language that contains no strings at all. It's denoted by the symbol phi. So here, the size is called the cardinality. We call it cardinality, which is the number of members a set contains. So it has no members, no elements in it. So it has a cardinality of 0. And for the empty string, denoted by epsilon, it's a string containing 0 symbols. So the length of the string is 0. So the empty string is a word containing 0 symbols. You can think of it like the character you get when you enter the space bar. And the empty set is like a dictionary with no words in it at all, not even the space bar. Powers of the alphabet. So the set of all possible strings of length k over an alphabet is called the power of the alphabet. So we can have alphabet to the power of k, where k can be any number at all. So it can be 2. In that case, it will be the set of all strings over the alphabet of length 2. Now the alphabet with the Kleene star is the set of all strings of all lengths over the alphabet, including epsilon, the empty string. So here it can include nothing at all. And the alphabet with the Kleene plus is a set of all non-empty strings over the alphabet.
So for more clarity, taking our alphabet as 0, 1, sigma to the power of 0 is the same as the strings of length 0, which is nothing but the empty string. And sigma to the power of 1 is also strings of length 1. So from our alphabet, there are only 2 strings of length 1, that's 0 and 1. Sigma to the power of 2, we can have strings like 0, 0, 0, 1, 1, 0, and 1, 1. And for strings of length 3, we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, and 1, 1, 1. They are all of length 3. So we can observe that once the length of the alphabet increases by 1, the number of its cardinality grows exponentially. So to determine the cardinality of any power of the power of any alphabet, the formula is 2 exponent k, where k is the length of the string. For the Kleene closure, it's equal to strings of length 0 in union with strings of length 1 in union with strings of length 2, and so on and so forth. For the Kleene plus, is equal to strings of length 1, strings of length 2, strings of length 3, repeating infinite times. But the difference is that with the Kleene plus, it doesn't include the empty string. There's no string of length 0. So that is the difference between the Kleene plus and the Kleene star. So we can implement the Kleene plus using the Kleene star in this way. We start by any alphabet and then we concatenate it with the Kleene star, forcing it to have at least one alphabet.
So let's move on to the 3 core operations. We have the union or the choice. It's represented with plus or the pipe sign. It represents the logical choice or alternation. It matches either the expression on its left or the expression on its right. So the syntax will be having our regular expression with a sign in between and having another regular expression on the right. Example, A union B. It matches either the symbol A or B. Concatenation. The symbol is either implicit or is the dot operator. So it joins 2 expressions in a fixed sequence. The string matched by the second expression must immediately follow the string matched by the first. So the syntax is that we can either put them in juxtaposition, having our first regular expression and the next, or we can use the dot symbol to show concatenation. An example, AB matches the symbol A immediately followed by B in that order. Repetition or the Kleene star. It specifies 0 or more repetitions of the preceding expression. It allows an expression to repeat any finite number of times, including 0 times. So the syntax is R star. Example, A star matches epsilon A, So what we are seeing here is that it matches strings of length 0, strings of length 1, 2, 3, 4, and so on and so forth. So aside these main operators, we can have some extensions to them. The Kleene plus is an extension. It specifies one or more repetition of the preceding expression. So we can still go on with this Kleene plus because it's equivalent to forcing at least one occurrence before applying the Kleene star. So the Kleene plus is equal to having an expression before applying the the Kleene star. An example, the Kleene closure of A matches A, A. So here we can see that the empty string is excluded, and that's the difference. We have the optionality operator denoted by the question mark. It indicates that the preceding expression is optional. It matches either 0 occurrences or exactly one occurrence of the expression. So why the optionality operator is considered an extension is because we can still represent it with the regular expression in union with the empty string. So the optionality of A matches either no occurrence or A. That's one occurrence. So these are 3 categories of questions we usually see on regular expressions. Boundaries and constraints. So it focuses on the rules governing character placement. We have the starts with question, the ends with questions, symbol containment, and does not contain, that's the forbidden string, substrings, positional locks. And the next group is the state and counting. It focuses on the quantity tracking, length limit parity, and modular arithmetic using finite memory states. So we can have questions like exactly 2 ones, at most 2, even number of zeros, and the modulo divisibility. And the last category is the structural patterns and dynamics. It focuses on global string textures, string alternation rhythms, repeating block doublets, and multivariable parity logic. So you can have questions like the uniform doublets, strict alternation, combined constraints, and the even zeros and even ones. So in our next video, we are going to solve the first group of questions.